explored Bloom filters, we looked at a quick way to check if data exists. But when the stakes are higher, a simple lookup tool is insufficient. You need a tamper-proof fingerprint. Looking at our algorithm map in the Cryptography and Data category, Algorithm 47 provides exactly that. This is the Secure Hash Algorithm, or SHA. It acts as the invisible glue for our digital infrastructure, fingerprinting every Git commit, validating TLS certificates for web traffic, securing blocks on the Bitcoin network. The architecture for this system was designed inside the halls of the U.S. National Security Agency. It was standardized as a universal tool by the National Institute of Standards and Technology. For over 2 decades, the Internet operated on a structural assumption that these early cryptographic fingerprints, specifically a version known as SHA-1, were mathematically invincible. That certainty ended on February 23, 2017, when researchers from Google and CWI Amsterdam announced they had successfully broken the algorithm. This diagram illustrates their attack, dubbed Shattered. Researchers engineered 2 completely different PDF files that produced the exact same SHA-1 fingerprint. It required over 6,500 CPU years of processing, yet was 100,000 times faster than brute force. This discovery forced major systems, including Git, to begin a massive migration. When 2 different inputs produce the same output, it's a collision. If an attacker can forge a duplicate fingerprint, the absolute certainty of data integrity is gone. The system can no longer be trusted. A secure cryptographic hash has a specific promise. It must be easy to compute in the forward direction, but computationally infeasible to reverse or intentionally collide. Its primary defense is a mechanism called the avalanche effect. This ensures that even the smallest change to an input causes a massive, unpredictable variation in the output. We can see this in action comparing 2 nearly identical inputs. We feed the word cat into the SA256 function, then the word cot. Despite only a 1-letter difference, the resulting hexadecimal digests share no discernible pattern. Roughly half the binary bits flip unpredictably. This lack of predictability is what mathematically prevents a hacker from reverse engineering the original input based on the hash they see. The modern SA2 family relies on the Merkle-Damgard construction, a step-by-step pipeline architecture. First, the algorithm takes a message and applies mathematical padding. It appends a 1-bit, several zeros, and the original message length so the data fits a strict block multiple. Once padded, the message is divided into discrete 512-bit chunks, creating a series of uniform blocks. The process begins with a running state called H0. It uses fixed constants derived from prime numbers, which feed into the first compression round. For each block, the algorithm runs 64 rounds of additions, XORs, and rotations. This process thoroughly mixes the running state with the current message block before moving to the next. Because every block chains into the next, a single byte chain at the beginning cascades through every round, resulting in a completely different final fingerprint. This design creates a mathematical gap. As shown here, SHA-256 processes data quickly in linear time. But for an attacker, the cost to defeat the math scales exponentially. We can see why SHA-256 became the standard. While MD5 and SHA-1 were compromised at lower work bounds, SHA-256 remains secure at a collision bound of 2 to the 128th power. Every single additional bit in the digest doubles the attacker's work. In Python, this immense security is accessible through the hashlib library. You simply update the object with your data and call for the hexadecimal digest. However, for passwords, we must add a defense called salting. This involves appending random characters to the plaintext before it ever reaches the hash function. Without a unique salt, identical passwords yield identical hashes. This would leave an entire database vulnerable to rainbow table attacks, where hackers match your user's hashes against a pre-calculated list. Today, SHA-256 is the standard for securing the internet. It drives Bitcoin's proof of work, authenticates software code, and protects secure web traffic. It has clear limits. Avoid MD5 or SHA-1 for any task requiring collision resistance. Furthermore, never store passwords with bare SHA algorithms. Use slow, memory-hard functions like bcrypt instead. Remember that a hash proves data integrity, verifying that a file is unchanged. It doesn't prove authenticity. To prove who sent the data, you need a digital signature. This exploration is based on 50 algorithms every programmer should know by Imran Ahmad. The code and research are available at neuralsca. Next, Algorithm 48, AES, the symmetric cipher used to encrypt and lock the underlying data.